Hi everyone! In this video we'll talk about linear functions and their applications. Linear functions in real life or an application, let's say such as business, usually we don't think of it as an equation. Well, we know several equations of lines that we've learned in the previous section, which is y equals mx plus b, and there's point slope, there's various equations. But if we have just data points and nothing else, which is usually in real life, like for example, you can plot cost versus, let's say, the number of items that cost you to produce or sell. So a linear function is a function that has a constant rate of change, which basically means it changes by the same amount of y versus x. Let's say every year, if something grows by the same amount, then it's growing linearly, and vice versa if it's decreasing. We'll talk about cost function in this video, which is, I usually describe it in my classes as c of x equals mx plus b. Hopefully this equation looks familiar to you. M we'll describe, which is the slope that may be familiar to you, but we'll also describe it as marginal cost, which the idea is it's the increase or decrease in cost for the next item or cost of producing one additional item. That's the definition we're going to use later in the course. For example, if we know marginal cost at a level of 100 items, how much it costs you, if we know the cost to produce 100 items, what would be the next cost, the approximate cost for the next item, such as 101st item. Now, for us, with the linear functions, marginal cost would be an approximate cost per item because it's always the same. It's sort of like the slope, how much it's changing by. And if it's always the same, then it's approximate cost per item. But a little bit later, of course, we'll know to produce 100 items may cost you, let's say, $5, and to produce 101st may cost you 20 cents, just because it's decreasing over time. Now, B is the fixed cost. This term may be familiar to you. Basically, it's the cost that remains constant either over a period of time, or a lot of times we're going to be thinking of it as the initial cost, sort of like the y-intercept of the line. So, revenue function, usually, again, we're going to talk about the basic situation here. Let's say we're selling a number of items and we're selling them at a certain price P, then the revenue would be the selling price P times X, which is the number of items. Basically, sometimes we'll think about it as demand times the price. And make sure you pay attention to how we set this up, because we'll use this definition of the revenue quite a bit later on the course. Break-even quantity, basically, how many items do we need to sell in order to match the revenue with the cost? So we're not making the profit yet, but another definition you can think of it as the profit is zero. So that's a couple of ways to solve for X. You can either set them equal to each other, or you can find the profit function, set it equal to 0, and solve for X. So profit, as you may well know, is basically anything left over once you make your revenue, which is basically the gross amount minus the cost, and so that would leave you with a net amount, which is the profit. So it's revenue minus cost. So we'll take a look at some of these problems here. For example, how do we write the linear function? Let's say Lake Tahoe Resort charges a snowboard rental fee of $10 plus $2.25 per hour. So if we define it as X is the number of items per rental, then it should make sense that cost function would be 2.25 times X plus 10, the flat fee on top of that. But let's take a look at the next situation. What if we make it a little bit more interesting? Let's say a parking garage charges $2 plus 75 cents per half hour. Now, what if we define X as a number of half hours? So see, it does make a big difference how you define the X. What if you define the X as number of hours? Then you have to convert into half hours, and your cost function may be different. But if we keep it simple, let's say X is a number of 30-minute periods, that you'll use, then the cost function would be 2 plus 0.75x. Now, we're going to learn how to find a cost function using the equation of the line learned in the last section. Say we know that we have a linear cost function. And what if we're given that the fixed cost is $100, but 50 items cost $1,600 to produce? Then we can write it as points. That's probably what I usually recommend to my students, probably the easiest way to do this, although there may be definitely several solutions for this problem. But if we think about this, the fixed cost is sort of like the y-intercept. It's the cost to produce 0 items, so it would be 0, 100, and the second point would be 50, 1,600 if we keep it as x comma c of x for the y. So we can find the slope, how we typically find it, which is 30, and that would be the approximate cost per item. And we can already write the equation, which is mx plus b, if you recall. So it would be 30x plus 100. So typically we're either given b and then we have to find the slope, or vice versa. Maybe we'll have the slope. Take a look at part B. Marginal cost is $75 and 50 items cost $4,300 to produce. So if you recall, the marginal cost for us would be slope m, approximate cost per item, and we can use the point slope equation. This is again one way I did it. You could also use y equals mx plus b and plug in x and a y to solve for it. That's another way to do it. So if the slope is given and I plugged in the point because we're given the slope and the point, so it makes sense to use the point slope equation. Y minus y1 equals to m times x minus x1. So if we plug this in and we solve for c of x, we obtain 75x plus 550. Now let's keep going. What if we have this situation? T-shirt cost. Joanne Wendell sells t-shirts at the community festivals and fairs. Her marginal cost looks like per t-shirt is $3.50, and her cost of 60 t-shirts is $300, and she sells them for $9 each. So I already wrote the result. How did I get the result? I basically used the point slope equation from the previous example, where 3.50, that's marginal cost, which for us is the slope, and then the point would be 60 comma 300, and again you can plug it in, and just like in the previous problem you can solve for it and hopefully you obtain the same result. The revenue, we know that the selling price is $9 each, so revenue would be 9x. And now we can set them equal to each other, and we can find out that x is 16.36. It's kind of strange to have a decimal point. Now typically, obviously we cannot have a decimal number of t-shirts. Now typically we would round down in a math class, but in a business class we usually want to err on the side of profit. So we're going to round up in this case. It's better to sell 17 t-shirts and maybe have a little bit of profit rather than the other way around. So we're going to round up just for the business, in the business sense. Now the next question would be, how many t-shirts must she produce and sell to make the profit of 500? And we can find the profit, which is basically revenue minus the cost, and we obtain 5.50x minus 90 equal to 500. So again, we obtain the result, which is 107.27, and we round up to get 108 t-shirts. Next concept that we'll discuss, that's from basic economics, is supply and demand, which can be defined in different ways. In this book, we're going to define it Q as the quantity produced or sold, basically number of items, and P is the price per unit. So there's various ways how you can set it up. You can, for example, set it up the quantity Q in terms of the price P, and some books would do that. Or you can do that the price depends on the quantity sold, for example, which is in this book, so D of Q and S of Q. So we have two different, linear equations in this section, the demand and the supply. Now, typically we know that the demand decreases as price increases from basic economics. but supply actually does it the other way around. So we'll see the graph on the next page. That's kind of the idea. If Q quantity is our X and P is our Y, which is how we define it, Q is our independent variable and P is dependent, then we have, let's say, two approximate graphs, and where they meet, or where the demand matches the supply, then we have the equilibrium quantity and price. So we can solve for Q first, say equilibrium quantity, the way we define it, which is our X, and then we can plug it back in into one of the equations since they're equal to solve for the price. And now, if we sort of to the left of this quantity, if we sell less, for example, and the price would be less typically, if the demand is higher than the supply, then we typically have a shortage. And if it's the other way around, if the supply is higher than the demand, because you may have, let's say, items left over sitting on the shelf, then you have surplus. That's how I remember. If the demand's higher than the supply, then you're outselling of the items, so you don't sell enough. So typically you want to match them. But here's how I define it. So surplus, so you basically compare demand versus supply at a certain price point or certain quantity point. So suppose we're given the demand equation, which is P, which is our Y, equals to 16 minus 1.25 Q, which is, notice how slope is negative. So P is the price in dollars and Q is the quantity demanded. Make sure pay attention to the units in this class, and it's in hundreds. Then let's say we know the price. We have the quantity and we have to find the price at each level. Say we have 0 watches and 400 watches. So how do we plug this in? Well, Q equals 0. It's very simple. We plug in 0 for the Q and we obtain $16 as the price if we don't sell any. Now if Q is, why did I set it to be 4? Because remember how we're talking about hundreds. So 400, it's 400, you can write it out that way, or it's 4 and then units are 100. So Q has to be 4, and we'll plug it in and we notice the price is 11. We sell 400 watches at 11. So let me actually add the 100 here. Let me pause it real quick. So as you notice how I wrote out the word, so 400 is equal to 400. But we must pay attention to the units. So if it's in hundreds, we have to divide by it, and we get that. So, and we go to the next page. I think we have the same kind of idea. Now, what if the price is given and we solve for the quantity? So we can set the equation equal to 8. Solve for it. Q is 6.400 or 640 watches. And same thing, we can set it equal to 10, 4.800 or 480 watches. And same thing with the supply. If the quantity supplied at each price, we can set it equal. Let's say we're given the supply equation 0.75 Q. Well, if quantity is 0, then it costs $0, then the quantity is 0 also. Now if it costs $10, then you can solve for it. And I believe we get 13.3300, or you can 1333 watches. And how we find the equilibrium quantity, we set them equal to each other, and Q is equal to 800 watches. Again, I must go back and forth, and we can plug it back in. I chose to plug it back in into the supply, and I got the price to be $6. That's kind of the optimal price, not too high, not too low. And that's it for this section.